Well, let's talk now about how we mathematically solve the semiconducting equations. Now, there are sort of two broad classes of semiconductor devices. There's one class that relies on minority carriers for their operation. Some examples would be solar cells or bipolar transistors. There are other devices that do not rely on the operation of excess carriers, in which there may be no excess carriers present, even under non-equilibrium conditions. I gave an example of that in the previous lecture, just a simple N-type resistor with two ideal contacts on it. In this lecture, we're going to focus on minority carriers and show how we can mathematically solve the semiconductor equations analytically, relatively simply, by making suitable approximations for minority carrier devices. So these are our equations. As we indicated before, it's a relatively complicated set of nonlinear coupled partial differential equations, but they can greatly simplify under certain common situations. In order to solve these equations, we basically have three options. We can do direct numerical solutions. You can solve these on a computer by discretizing the equations and solving the resulting systems of equations. Computer programs to do that are widely available. We can also get qualitative solutions. We learned how, by drawing an energy band diagram and interpreting it, we can understand what the qualitative solutions are to problems like this. A third option is to simplify these equations appropriately so that they can be solved analytically relatively easy. That's what we're going to be discussing in this lecture. So this is going to be a lecture that will come down to focusing on minority carriers. We will show how these equations can be simplified to an equation that we call the minority carrier diffusion equation. It's important for certain devices, so-called minority carrier devices, and I'll present several examples of how we can solve this minority carrier diffusion equation under a variety of different assumptions. These examples are very similar to the homework assignment for this unit, so you can see more details of the solution by studying those solutions and working those homework problems. All right, so let's see how we can simplify our semiconductor equations to describe minority carriers. So I'll assume, to be specific, that we're going to be discussing an N-type semiconductor, and we're interested in the minority carrier holes in this N-type semiconductor. We'll assume it's in low-level injection, so the electron density is going to be what it was in equilibrium. We don't need to solve any equations for that. We will be solving the hole continuity equation and focusing on the minority carriers for holes. Now, we'll make an assumption that there's only one dimension in which things are varying spatially. And I'll write G as G sub L to denote that I'm going to be thinking about the generation processes as optical generation of minority carrier holes. Now, we're going to be assuming low-level injection. So the minority electron concentration is not perturbed. We're not even going to worry about electrons. The minority hole concentration is overwhelmed by these excess minority carriers, so we'll simply solve for the excess minority hole concentration since the equilibrium concentration is insignificant. I'm also going to assume that we have a situation in which we're perturbing it with small numbers of positively charged excess holes. Usually there's a small number of corresponding negatively charged electrons, so the two counteract each other. There aren't large charges or electric fields that get built up. So I'm going to assume that there is no electric field to worry about. So when I write my drift diffusion equation, a drift part due to the electric field and a diffusion part due to the concentration gradient, I can neglect the drift part, ignore the electric field component, and simply treat the diffusion current. That is the current that is going to dominate in these problems. And then I will assume that my diffusion coefficient is independent of position. It's just a material-dependent constant. The minority hole concentration might vary with position, but the diffusion coefficient doesn't. I can pull it out of the differential, and I end up with an equation like this. That's my highly simplified hole continuity equation for this problem. That equation is encountered frequently, and we call it the minority carrier diffusion equation. So this is the equation that we're going to discuss, and we're going to try to learn how to solve it under certain important, simple conditions. Now, when we're solving a problem like this is actually a reasonably complicated partial differential equation itself. Has both time and space dependence. We'll need to specify an initial condition and boundary conditions. The solutions in general can get quite complicated, but under a few simple cases, they become really very simple and easy to do. If we're encountering a problem, the first thing we would do is to check and make sure that the simplifying assumptions that I just went through in order to simplify the whole continuity equation to this minority carrier diffusion equation, we first need to assure ourselves that those simplifying assumptions are correct. Then we need to examine the problem. We need to specify the initial conditions and the boundary conditions. Sometimes we can further simplify the equation given the specific specification of the problem and then solve that equation. Okay. Just a reminder, we're going to be talking about low-level injection in an N-type semiconductor. That means the excess carriers have an insignificant effect on the electrons. But the excess carriers have a huge effect and overwhelmed the equilibrium density of minority carrier holes. We would be solving then a minority carrier diffusion equation to understand the position and time dependence of the minority carrier holes in this N-type semiconductor. In a P-type semiconductor under low-level injection, it's similar. The excess carriers don't perturb the hole concentration, they're majority carriers. They greatly perturb the minority electron concentration, and we would solve a minority electron minority carrier diffusion equation to address this problem. We're going to be focusing specifically on electrons and P-type electrons in P-type silicon. Just to put some numbers in, we'll assume that this P-type silicon is doped at 10 to the 17th per cubic centimeter. We'll assume a mobility of 300 centimeters squared per volt second, which is a reasonable number for this doping density. We will need the diffusion coefficient. We get that from the Einstein relation. So the diffusion coefficient is about 8 centimeters squared per second. We will need to know the minority carrier lifetime, whether it's due to Shockley-Reed-Hall processes or whatever. In this case, it would most likely be defect-assisted Shockley-Reed-Hall processes, and I'll assume that the minority carrier lifetime is 1 microsecond. That's not an extremely short time. It's also not an extremely long time. It's possible actually to get milliseconds lifetimes in high-quality crystalline silicon. And there will be a parameter that we will see that will become very important. It will be the square root of the product of diffusion coefficient times minority carrier lifetime. The diffusion coefficient has units of centimeters squared per second. The lifetime has units of seconds. D tau has units of centimeters squared. Square root of d tau has units of centimeters or meters or micrometers. If we put numbers in, we'll find that this minority carrier diffusion length that we will encounter in this problem has a numerical value of 28 micrometers. Okay, so now we're going to go ahead and solve this problem with these numerical parameters under a number of different situations. So let's look at the first example. First example is very simple. We'll assume that it's steady state. We're shining light on this P-type semiconductor. We've been doing it for a long time. It's a uniform problem. It's a uniform generation of carriers. There is no spatial variation. The optical generation rate will be 10 to the 20th carriers per cubic centimeter per second. And we'd like to solve for the minority electron concentration and for the quasi-Fermi levels in this problem. Okay, so our approach, we simplify the minority carrier diffusion equation for this specific problem. We then solve it, and then we deduce the quasi-Fermi level from the resulting excess minority carrier concentration. So we're going to solve this minority carrier diffusion equation. We're in steady state. This problem specifies steady state, so there's no time dependence. This is a uniform problem, so there's no space dependent. So this minority carrier diffusion equation simplifies greatly. And we can solve that equation easily. We find that the excess minority electron concentration is just G sub L tau, generation rate times the minority carrier lifetime. So this is a very simple problem to solve. Okay, it's worth remembering this result because you'll encounter this from time to time, and we can remember what the solution to this problem is. It'll save us a little bit of time. So this uniform semiconductor extending to plus infinity, minus infinity, our excess minority electron concentration will have no spatial dependence. It will just be equal to G sub L tau. Put numbers in and we'll get 10 to the 14th excess carriers per cubic centimeter in the semiconductor. So we've generated a uniform concentration of minority carriers. So now to deduce the Fermi levels, quasi-Fermi levels, let's go back to the equilibrium case before we turned the light on. We had a p-type semiconductor doped at 10 to the 17th. The minority electron concentration in equilibrium is just 10 to the 3rd per cubic centimeter. If we want to deduce the Fermi level, we can set 10 to the 17th equal to Ni times e to the Ei minus Ef. We can solve that equation. We'll find that the equilibrium Fermi level is down here 0.41 electron volts below the intrinsic level. That's the situation before we turn the light on. Okay, now out of equilibrium, nothing really changes for the holes, but a lot changes for the electrons. Okay, so our whole quasi-Fermi level is going to be 0.41 electron volts below the intrinsic level, just where the Fermi level was in equilibrium. For the electrons, we will relate the electron density to the electron quasi-Fermi level with this expression. We'll put numbers in. If we solve for Fn, we find that it is 0.24 electron volts above the intrinsic level. So this is reflecting the fact that we have many more electrons now than we did in equilibrium. So our quasi-Fermi levels are split. Fn is greater than Fp, so Np is much greater than the equilibrium Ni squared product that we had. All right, that was a simple problem. Now let's take that problem and let's just turn the light off. We'll turn the light off and see what happens. So this will be a transient problem. There won't be any generation. We've turned the light off. We didn't have any spatial variation to begin with, and there's nothing to induce a spatial variation as time progresses, so we won't have any spatial variations either. Again, we'll simplify the minority carrier diffusion equation for this problem. We'll solve it, and then we can deduce the quasi-Fermi level as a function of time now because we have a transient problem. Here's our minority electron diffusion equation. This is a problem in which there is a time dependence, so we can't throw that out. There is no spatial dependence, so we'll have a 0 there. The minority carriers will recombine, but we have turned the light off, so we have 0 generation. So we have an equation. We have a simple differential equation. That's one that we can look at and recognize that the solution to an equation like that is an exponential solution. There will be an e to the plus t over tau and an e to the minus t over tau. We throw out e to the plus t over tau because that would grow with time. We know physically that what's going to happen is that the excess minority carriers are going to decay and vanish with increasing time. So the solution will be delta n at t equals 0, the 10 to the 14th per cubic centimeter that we obtained when the light was on, and then it will decay as e to the minus t over tau, where tau is 1 microsecond. All right, that's our solution under these conditions. If we plot the excess minority carrier concentration versus time, it began at 10 to the 14th when the light was on. We turned the light off. It decays as e to the minus t over tau. The semiconductor is restored to equilibrium where it was before the light was turned on to begin with. Okay, if I plot delta the excess minority electron concentration versus position, it's just uniform, independent of position. At t equals 0, we had 10 to the 14th of them, and that number then will just decay as e to the minus t over tau until all of the excess carriers are gone. Okay. Now the question, the final question we have is, if we're interested in how the quasi-Fermi levels vary with time, can we deduce that? And yes, we can. Here's the location, here's an energy band diagram showing the quasi-Fermi levels when the light was turned on. Now we switch the light off and we ask what happens. Well, nothing is going to happen to the whole quasi-Fermi level because it didn't change in equilibrium, out of equilibrium. It's just going to stay where it was. But the electron quasi-Fermi level has to eventually end up where the whole quasi-Fermi level is, and they will both be equal to they will both return to the Fermi level in equilibrium. Well, we know there's a relation between n and the quasi-Fermi level. We know that n is, to a good approximation, equal to the excess minority carrier, minority electron concentration. We know what that is. We'll put in our solution to the minority carrier diffusion equation. We'll equate it to this expression that is in terms of the electron quasi-Fermi level, and we will be able to solve. We will find that the electron quasi-Fermi level is where it was at time t equals 0, and then it decays linearly with time. It'll simply drop as time progresses until it drops down and hits the quasi-Fermi level for holes, and everything settles back into equilibrium. Now, it might bother you a little bit, so we should stop and think just for a minute. For very long times, if we wait till t approaches infinity, the electron quasi-Fermi level has to relax back to the whole quasi-Fermi level. They're both at the Fermi level for the equilibrium semiconductor. This equation, if I continue it out to t approaches infinity, is not going to stop anywhere. It's just going to continue to get more and more negative. So there is some problem with my derivation. Look back and think about this a little bit. We made an approximation that works fine for the initial stages of this, but that doesn't describe the final stages of that decay. See if you can think about that and figure out what's going on there. All right, so that's a way that after we solve the minority carrier diffusion equation, we can always then translate that minority carrier diffusion minority carrier concentration to a quasi-Fermi level. All right, let's do actually three, I believe, more examples, because these are important examples also. This will be a steady state problem. Well, steady state, no time dependence. It'll be a sample that is very long. And as you'll see, what I mean by long is long compared to this minority carrier diffusion length that we introduced. We'll assume it's 200 micrometers long. There will be no optical generation in this problem. And we will specify two boundary conditions. So we will have some means, and there are ways to do this, that we can fix the minority electron concentration at x equals 0 to be 10 to the 12th electrons per cubic centimeter, and it will just be constant, independent of time forever. And we will fix its value at 0 at the end of the sample, 200 micrometers away. And then the goal is to solve for the electron concentration and for the quasi-Fermi level. We'll be solving this minority carrier diffusion equation. All right, we'll go through the same steps. We'll notice that this is a steady state problem, so there's no time dependence. There will be a spatial dependence, so we have to retain the second derivative with respect to position. There will be recombination that will occur. We can't throw that term out. But we said that there's no generation, so we can set G sub L equal to 0. So we'll have to solve this equation. If I rearrange that equation a little bit, I can write it this way. I see these constants here, d tau, that have the units of length squared. D times tau is what we call minority carrier diffusion length squared. So we can simplify the equation and write it in this form, where L is the square root of d tau, this minority carrier diffusion length that we introduced earlier. So we have a simple equation to solve. This is a second order differential equation. We have two boundary conditions. We specify the concentration at x equals 0. We specify the boundary condition at x equals L. But you know, 200 micrometers is so much longer than the diffusion length, which you'll recall when we put numbers in, is 28 micrometers. So it's so much longer, we can just think of L as approaching infinity. So the way we'll interpret this boundary condition is that the solution approaches 0 as x approaches infinity. Okay, well, we can check by plugging these assumed solutions back into this equation that e to the plus x divided by e to the minus x divided by diffusion length and e to the plus x divided by diffusion length, both of those solutions satisfy this second order differential equation. Now, as L gets very, very long, this second term would grow and become very long and would never satisfy this second boundary condition. So we can throw out the second term. The constant b is 0 in this problem, and we only have the first term. The first term, then, we can specify the value of a, the constant, by making sure that we satisfy the first boundary condition. And we will find that our solution to this problem is just the value of the electron concentration, the excess electron concentration, at x equals 0 times e to the minus x over diffusion length. Okay, so we have a simple exponential solution to this example. If we plot the steady state excess electron concentration versus position in this sample, it'll simply decay from its value at x equals 0 as e to the minus x over diffusion length, and then reach infinitesimal values deep into the semiconductor, essentially 0. So we have nice, simple exponential solutions in space, not in time now. This is a steady state problem, so this is the steady state solution. The characteristic length for problems like this, when carriers are diffusing spatially, is the diffusion length. And when we put numbers in, that's 28 nanometers. That tells us the length over which the minority carrier concentration can vary. So when there are spatial variations and we solve this differential equations, the spatial variations will take place on the length scale of the minority carrier diffusion length. All right, now, you could also translate that minority carrier electron concentration into a quasi-Fermi level and plot that on an energy band diagram. I'll encourage you to think about doing that. I'll give you an example in another example in just a few minutes where I'll show you how we can do that. So let's move on to another example. This is exactly the same example as in example 3. It's just that the length of the semiconductor is much shorter. I'm going to assume it is 5 micrometers now long, not 200 micrometers. Now that's significant. 5 is much less than the 28 nanometer diffusion length. This is very short compared to a diffusion length. The previous example was very long compared to a diffusion length. Same boundary conditions on both ends. We'll have the same differential equation to solve. We just have a different length of structure. Okay. Now, when we do this, we're going to notice the diffusion length is very long in this case compared to the length scales. That means, what that essentially means is that carriers will diffuse without recombining across the entire 5 micrometers. They'll get from one end to the other without having any significant chance of recombining. That means we can throw out the recombination term. It's not important in this solution. That means we get an even simpler equation. We get the second derivative of delta n with respect to space is equal to 0. Okay. So that's a differential equation that we need to solve, subject to these two boundary conditions. The solution to this differential equation is not an exponential. In fact, you can see that any linear function satisfies that equation. Just plug in a linear function, differentiate it twice, you'll see that you get 0 equals 0. Now, in order to determine the two constants A and B, we simply evaluate this electron density at x equals 0 and set it equal to delta n at x equals 0. And we evaluate it at x equals L and set it equal to 0 at x equals L. We solve for the two constants A and B, and we'll find that our solution is delta n of 0 times 1 minus x divided by length. A linear solution to the differential equation in this case. Okay, if we plot that, we have the same boundary condition we did in the earlier example. We have the same boundary condition here, but in this case, we do not get exponential solutions. We get linear solutions. The minority carrier concentration just goes linearly from its value at the left to its value at the right. These are the kinds of solutions that we get when the semiconducting region is short compared to a minority carrier diffusion length. Our sample is only 5 micrometers long. The diffusion length is 28 micrometers. Physically, what that says is that if electrons come in, they diffuse across and they never recombine because the sample is so short, they cross the device without recombining. All right, so that's a particularly simple example. Let's do one more example. We did one that was long. We did one that was short. We should do one that is in between. So let's take 30 micrometers. 30 micrometers is about 1 diffusion length long. So this solution will be between the exponential and the linear. Again, we're solving the same minority carrier diffusion equation with the same simplifications. We end up with a simplified form that looks the same. It's just that now the diffusion length is about the size of the sample. We can't assume it's infinitely long. We can't assume that it is very short. It's in between. Well, when we solve this, we will get solutions of the form e to the minus x over diffusion length and e to the plus x over diffusion length. We are not allowed to throw away either of these. We will simply evaluate this quantity at each of the 2 boundary conditions, and doing that, we can determine the 2 constants, a and b, and then we have our solution. If you rearrange these exponentials and write them in terms of hyperbolic signs, we'll find that the solution looks like this. A little bit hard to see exactly what that looks like. What we would have to do is to plot it. Remember, in the case in which the region was short, we just had a straight line. If we plot it in this case, we'll find that we have some slope to the straight line. If we were to make the diffusion length shorter and shorter and shorter, we would find that this would become an exponential that would decay to 0 eventually. So this is an example between the case of long and between the case of short. It gets to be a little bit more work to solve this because we have to include both terms, but the procedure is the same and the final solution that we get looks similar. I mean, looks physically plausible and we can understand what's going on. All right, there's one final example that I want to go to, and then, we've seen a collection of examples for minority carriers that we could then, if we encounter a minority carrier device, we'll have some good intuition as to what the solution will look like. So this is an example. The sample is infinitely long, goes to x, we let x approach infinity. It's uniformly illuminated with light, like the first example we had. Same optical generation rate that we had in the first example. The minority carrier lifetime is a microsecond, just like it was in example 2. But in this case, at x equals 0, I'm going to have a surface, and I'm going to assume that that surface is highly defective. A highly defective surface will introduce a lot of defects in the forbidden gap that will facilitate the recombination of minority carriers. Let's assume that the surface is so defective that it forces the minority carrier concentration to be 0 there. Any minority carrier that encounters that surface immediately recombines, so the minority carrier concentration at x equals 0 is 0. That's our boundary condition. Okay, so find the steady state minority carrier concentration versus position. I'll get this same steady state equation that we've been dealing with in the previous 2 examples, but now I have light shining, so I'll have to include the optical generation rate there as well. I could go ahead and I could solve this differential equation. It's just a little bit more work now because it's what we would call an inhomogeneous equation. We have a forcing function here, the optical generation term, but it's an equation that we could solve. But it's also an equation that you could probably guess the solution using the intuition we've had from earlier solutions. Let's see if we can do that. So here's our surface at x equals 0. X goes off to infinity. This is the differential equation that we need to solve. But if we're clever about things and use the intuition from solving simpler problems, we can sort of see what's going to happen. My boundary condition is that my defective surface forces the minority carrier concentration to be, the excess minority carrier concentration to be 0 at the surface all the time. Now, deep in the bulk, you remember the very first problem that we encountered. We had an infinite semiconductor with a uniform generation rate. We said that the minority electron concentration that's produced by that optical generation is G sub L tau. That was the steady state solution. This is a steady state problem. If I go deep in the semiconductor, I would expect to find that solution again. How deep? Well, I would have to go a few diffusion lengths deep, because the characteristic length scale in these problems is the minority carrier diffusion length. So I can sketch the solution. I know it's 0 at the surface because of the defects. I know it's G sub L tau in the bulk. I know it's going to smoothly go from one to the other. I know that this distance is going to be on the scale of a diffusion length. I expect the solutions to go exponentially with diffusion length, because that's what comes out of a differential equation like this. I could actually just guess the solution. G sub L tau times 1 minus e to the minus x over minority electron diffusion length. That would be my solution. It does just what it's supposed to do. That's what the solution to this problem would look like. Now, we could ask, how do we draw an energy band diagram with quasi-Fermi levels for this case? So to do that, remember there's no electric field. That's my assumption when I'm using this minority carrier diffusion equation. The fact that there's no electric field means that there's no slope to the valence band or to the conduction band. The bands are flat. Okay. This is a p-type semiconductor. So the quasi-Fermi level for holes is down near the valence band, and it hasn't been perturbed by this light that is shining on the semiconductor, so it's flat, just where it was in equilibrium. But deep in the bulk, I have a lot of excess carriers generated. Near the surface, or at the surface, I have no excess carriers. When I have no excess carriers, F sub n must equal F sub p. F sub n will smoothly go from its value at the surface to its value in the bulk. The length scale will be the minority carrier diffusion length. We could find the equation that describes this just by solving the previous equation we had for the minority electron concentration and deducing from that solution the corresponding electron quasi-Fermi level. So that's what it would look like, and oftentimes we will draw energy band diagrams out of equilibrium and indicate the quasi-Fermi levels intuitively where we expect them to be in order to help us understand the operation of devices. Now, there's a gradient of the quasi-Fermi level here. That means there's an electron current in this problem. That represents the flow of electrons to the surface as they recombine and continue to, they're generated in the bulk, they diffuse to the surface and continually recombine under these steady state conditions. That gives us a current towards the surface. All right, so let's wrap up this lecture. We've been talking about how we solve these semiconductor equations under conditions in which we can simplify them so that analytical solutions are relatively easy to do. The particular simplifications had to do with low-level injection of minority carriers. We can do that in an N-type semiconductor or a P-type semiconductor. Assuming that there's no electric field present, then that makes the solutions relatively easy to obtain. And these are common situations for minority carrier devices like solar cells, bipolar transistors, for example. And finally, the general characteristics of these minority carrier diffusion equations, when we solve them, we've seen by several examples what the general characteristics of the solutions are. Sometimes the differential equations can be a little bit complicated to solve. We have to refresh our memory on solving partial differential equations. But the qualitative form of the solutions is easy to sort of anticipate from these simple examples that we've discussed. Transient solutions tend to go as e to the minus t over minority carrier lifetime. Spatial solutions go exponentially as e to the minus x over diffusion length when the sample is long. Steady state spatial variations go linearly when the regions are short compared to a minority carrier diffusion length. Okay, so the purpose of this lecture was to illustrate how one can simplify the semiconductor equations in certain situations and then solve them analytically. It was also to illustrate what some of the solutions to this minority carrier diffusion equation look like, because this is an important equation when we encounter minority carrier devices. So this completes the lectures in Unit 5 on these semiconductor equations and how we solve them. I will continue and just recap in the next lecture some of the key points that we should take away from Unit 5.